Hey guys, welcome back to Bottom Up Chem. This is the second video for Unit 9 and Unit 19, that's redox processes. And we're going to be looking at redox equations. So we're going to be looking at taking the skills that we looked at in the first lesson and building on them for whole systems. Let's get right on with it. So today we're going to be looking at defining what redox equations are, what half equations are and how to write those, and then how we can combine those to formulate balanced redox equations that are in acidic or in alkaline conditions. As usual though, we got a refresh question for you to get started on, which is based around deducing the oxidation states of nitrogen in nitrate and nitrite. Pause the video here to give yourself a moment to try that. Brilliant. So hopefully you can see here we've got nitrate, nitrite. We have NO3, which gives overall charge of -1, which means our nitrogen is going to have an overall oxidation state of +5. Our nitrite ion has the same overall charge, -1, but less oxygen. So our nitrogen is going to have an overall charge of +3. Okay, on to redox equations then. So whenever oxidation occurs, we also have reduction occurring. These processes can't be fully separated. So let's take the example here of zinc and copper ions. So copper will gain some electrons and zinc will give up its electrons. But if we have a look at our oxidation states, we've got 0 and +2 and then 0 and +2. So we can see that zinc goes from a 0 oxidation state to +2. So it is oxidized. And we can see that copper goes from +2 to 0. So 0 to 2 is an increase in the oxidation state. So that is oxidized. And copper goes from 2 to 0. So it is reduced. The number reduces. Now, perhaps this is counterintuitive, but we call the thing that is oxidized, in this case zinc, the reducing agent. And the reason we do this, if you think about it, is clear. It's because it is causing the copper to be oxidized. So the thing that is reduced is called the oxidizing agent, and the thing that is oxidized is called the reducing agent. So copper 2+ is our oxidizing agent in this case, as it gets reduced. So that can be a little bit counterintuitive to begin with, but just make sure if you're asked for an oxidizing agent or a reducing agent to just be careful of that inverse relationship. There's a special type of reaction, because I've said that we can't have reduction without oxidation, called a disproportionation reaction. And so I'm going to use the example here of the breakdown of hydrogen peroxide to demonstrate this. So if we start calculating the oxidation number, we can see we have +1 and -1, +1 for hydrogen. So we see no change in the hydrogen. Now, so it can be tempting to think, well, there mustn't be a redox equation here because we have to have both. But let's just turn our eye to that oxygen and see what happens to that. So we have a -1 oxidation state, but in the water, it goes to -2. So that's fine. We can see that's a reduction. And if we look at the oxygen produced, oxygen obviously has an oxidation state of 0, so that is oxidized. So that means that some of the oxygen atoms are being oxidized and some are reduced, hence disproportionation. Just to remind you, and this is kind of a definition, that oxidation is always going to be associated with an oxidation number going up, and reduction is always associated with a number going down. Hence we can see that oxygen is disproportionately oxidized and reduced in this case. Right, so let's have a look at an example. So we can look at a really common reaction. So this is the extraction of iron from iron oxide using carbon monoxide. So we'll write out our balance equation here, and let's have a look at some of the oxidation states. So we see that oxygen here is -2, iron is therefore +3, oxygen also -2, and carbon therefore +2. Now we've got elemental iron, which is 0, oxygen +2, and carbon +4. So iron goes from 3 to 0, so therefore it's reduced, it's going down. oxygen's all staying the same, and carbon's going from +2 to +4, which is oxidized. And that's how we can use these equations to tell what's going on in the reaction. So now you can say in this reaction, we show the reduction of iron and the oxidation of carbon. Looking at another example then, let's have a look at the displacement of copper from copper sulfate by zinc to make zinc sulfate and copper. So sulfate ion always has -2 altogether. So we've got +2 from copper, 0 for zinc. That means we got +2 for zinc in the product. So copper goes from +2 to 0. Again, we've got a reduction because we're going down, and zinc is going up. So zinc is being oxidized. So we can say that in this reaction, we can see copper being reduced and zinc being oxidized. Let's have a go you doing some questions then. First question, in the following reaction, identify the change in oxidation states. Pause the video here to give yourself a bit of time for that. Pop them up. Brilliant. So hopefully for that you saw we had iron being +3 in the reactants, aluminium being 0, and then aluminium being +3 and iron being 0 in the product. So iron going from +3 to 0 is of course being reduced, acting as the oxidizing agent, and aluminium going from 0 to +3 is oxidized. Next question then. Same thing here, identifying oxidizing and reducing agents in this acid-base reaction. Pause the video here to give yourself a moment for that. Pop them up. Once again, the best thing you can do is of course go through, label all the oxidation states in all of the molecules so you can see where the changes are actually occurring. So after I've done that, we can see that hydrogen, oxygen stay the same, but what's really happening is sulfur is going from +6 to +4, so it's being reduced, and bromine is going from -1 to 0, so it is being oxidized. So sulfur is our oxidizing agent, or H2SO4, the molecule it's in, and the HBr or Br- is our oxidizing agent. So this is all very well, but as we've already started to see, we've got a lot going on in these, and we may want to reduce the amount we have to look at, and that's where half equations really come in and simplify things. So reusing this equation that we've already had a look at, we know that we've got iron is being reduced and aluminium is being oxidized. But now we're going to write it in a slightly different way, and you can see, okay, what explains what's going on here? Well, iron must gain some electrons. It's going from 3+ to no charge, and aluminium must also lose some electrons. So we can see that how I've balanced that equation with electrons. Now, this is a very simple example, but this allows us to make very simple versions of complicated systems. Now, in this example, we only needed electrons to fully balance our half equations, but we're going to go through a stepwise process that's going to allow you to balance any half equation that you come across. And it's made up of 5 steps. So the first step is you're going to balance the equation, everything apart from hydrogen and oxygen. Then you're going to use water to balance oxygen, H+ to balance hydrogen, and electrons to balance charge. And if you need to, you're going to use OH- to balance the H+. Now, we're going to assume that the question is always in acid solution unless you're told otherwise, but we'll go through the methodology anyway. As always, this is probably going to be easier to understand using an example. So let's use a simple example first of iron ions turning into iron metal. So that's Fe2+ goes to Fe. Now, we'll look at our steps. Well, step 1 is kind of already balanced. Step 2, not applicable. We don't have any oxygen. Same with hydrogen. Now, step 4, however, we have on the left-hand side a +2 charge, and on the right-hand side a 0 charge. So we have to add 2 electrons to the left-hand side to balance that charge out. And as I've said before, we don't have to worry about hydroxide ions unless the question specifically says in alkaline solution. So let's have a look at another one that's a bit more difficult. So here we're looking at MnO4 minus ions turning into Mn2 plus ions. Now, step 1 is already done for us because I have one Mn atom on both sides, so that's done, and I don't have to change those. Next, I can move on to oxygen. Now there's 4 on the left, so I'm going to add 4 water on the right. Now that I've added those water, however, I've added 8 hydrogen atoms, so I'm going to add 8 H plus on the other side of the reaction. So with step 3 done, now I want to calculate the charge on both sides. So on this side I have plus 8 minus 1, so I've got plus 7. On this side I've only got plus 2. And the only thing I can do is add electrons, which are going to reduce charge. So I'm going to need to add 5 electrons to my left-hand side, which is going to balance the charge. Again, we're going to assume that we don't need to account for alkaline solution, and that is a fully balanced half equation. Let's get you doing a few questions. First question, write the half equation for the reduction of Fe3 plus to Fe2 plus ions. Pause the video, give yourself a moment to try that. Pop them up. Nice simple one to start, going through your steps, writing the equation out. Initially, it's already balanced in terms of atoms. There's no oxygen, no hydrogen, so you're just going to need to add 1 electron to your left-hand side, and again, nothing alkaline here. Next one, bit more difficult, is the chromate ion. So take your time and go through all 5 steps here. Pause the video to give yourself a moment for that. Pop them up. So with this one, be careful that you don't miss your first step, because if we put our chromium ions, 3+, we need to first of all balance the equation, which is going to put 2 chromium ions on the right hand side. Start with my oxygens. We're going to need 7 waters. That's going to give me 14 H+ that I need to add to the other side because it's H2. And then I'm going to calculate my charge for step 4. So I've got plus 12, 14 minus 2 on this side, and I've got plus 6. So I need to reduce the side on the left by 6. So I'm going to add 6 electrons to the left-hand side. Fantastic. Again, nothing to do with alkali here. Okay, so we're really getting stuck in now, and now we want to learn how we can combine these individual half equations to produce an overall reaction that tells us exactly what is happening in a given reaction. And all we have to do is combine both equations by making 2 equations have the same number of electrons, and we're just going to multiply through to do that. Once again, we're always going to assume that we've got an acidic solution, but if the question does say that we've got an alkali solution, all we're going to do is we're going to add as much alkali that will remove the H+ from the equation and make it alkali. We're going to add it to both sides of the reaction. I'm going to go through examples of all of this, so let's have a look at first simple example. So combining here, it wants us to look at how bromine will oxidize sodium. So I'm going to draw half equations for both of these. So we've got Br2 is going to go to Br minus. I'm going to need to go through my steps. I'm not going to go through each of the steps here. If you're still struggling with half equations, go back and have a look. So we get our 2 balanced half equations, and this is the important part. What do I notice here? The top equation has 2 electrons and the bottom has 1 electron. So when we combine these, we're not allowed any electrons left over in the equation at the end, because electrons don't really roam around by themselves. That's just not what's really going on. So what we're going to do is we're going to take that bottom equation and we're going to multiply it by 2. We're effectively going to give them the same coefficient, which when we combine them means that the things on the left and the things on the right of the equation will cancel out. And that means to express our final redox equation, all we have to do is we take the things on the left of the equation and they go on the left and make our reactants. And then we take the things on the right and we add them together. And again, the electrons are on both sides, so they cancel out. And that gives us our final overall redox reaction. So let's have a look. Another example here. Again, an inacidic solution, but slightly more advanced half equations. But it's still no issue for us. Again, in constructing the half equations, we're going to do our 5 steps. We're going to balance the equation, which already is here. We're going to use water to balance our oxygens. Then we're going to use protons, H+, to balance our hydrogen. And then finally, electrons to balance the charge. We can go through that process with both of our half equations. And then we've got 2 half equations that we want to combine. Now we'll see here that we've got a difference. So we're going to multiply that bottom equation by 5. And then that means the electrons will cancel out. And everything on the left-hand side of both equations will then be part of our reactants of our overall redox equation. And everything on the right-hand side will be part of our products of our overall redox equation. So initially, this might feel like it's taking a lot of time, but that's fine. Just stay with it. With a bit of practice and just following those steps, it will soon become second nature to go through it. So let's have a look at boss mode, highest level kind of question you can be asked, which is something to do with this little alkaline solution that's been twinkling its eye throughout the lesson. Once again, I'm going to make balanced half equations going through that 5-step process, water, H+, and then electrons to balance it out for both of our half equations. I've got my hydroxide breakdown equation, and then I've also got Fe2+ being transferred to Fe3+. So I'm going to write that half equation. Then, as normal, as we just did twice in a row, we're going to combine those by multiplying to get the same number of electrons. So that gives us, we're going to need to multiply that second equation by 2. And once we combine that, that's where we were before. That's an acidic redox equation. So this equation that we're writing now would be correct if it was in an acidic solution. So what do we do to get it in an alkaline solution? Well, all we're going to do is we're going to add OH- to both sides. And how much do you add? Well, all I'm trying to do is trying to remove my H+ ion. So I'm just going to here add 2 moles of OH- to both sides. So let's just do that. It's the same equation written out on both sides. So now I have 2 OH- on my left-hand side, and I'm also going to add 2H- to my right-hand side. And this equation as it is not necessarily incorrect. However, it's not in a simplified form. So let's just quickly have a look at some things that we might highlight here. Well, we've got H+ and OH- on this side. So they're going to combine to give us 2 moles of water. Then we can write the equation out as it was. And we're almost done, except we might notice that on both the left and right hand side, we have water. So that doesn't make any sense. So we can just cancel those out like the electrons. So now we see that H2O2 reacts with 2 Fe2- to produce 2 Fe3+ and 2 OH-. And that is our overall equation in an alkaline solution. And yes, this one is more involved, but again, following your steps and you'll still come to the correct answer. So let's do a few questions on that. First question, I want you to write the overall redox equation when iodine oxidizes copper. Pause the video here to give yourself a moment for that. Pop them up. Brilliant. So these already are balanced in terms of the actual individual equations. We just need to multiply the top one by 2 and then add it to the second one. So we end up with I2 plus Cu. Electrons cancel out and we get I- plus Cu2 plus. Have a go at this one, which you're going to need to balance first. Pause the video here to give yourself a moment for that. Pop them up. Brilliant. So hopefully you saw that in the top equation, you're going to need 2 electrons to balance your copper. And in the second equation, you're going to need 1 electron on the right hand side, and of course to multiply that second equation by 2, which is going to give you H2 goes to 2 H plus and 2 electrons. Your electrons are going to cancel out, and then you just write the equation out by adding them together. Okay, a little bit more complex one, but you don't need to balance these, they're already balanced for you. Pause the video to give yourself a moment for that. Pop them up. So here we see that we've got 5 and 2 electrons. So obviously 2 doesn't go into 5. So I'm going to find the lowest common factor. So I'm going to multiply the top one by 2, the bottom one by 5. And that's going to allow me to have 10 electrons on top, 10 electrons on the bottom. And once we've got the number of electrons the same, that means we're going to be able to cancel them out. So an easy way to remember this is if you get this in the future is you can just multiply each equation by the number of electrons in the other equation. And that's going to give us this final overall equation. Just make sure you cancel out your electrons so the electrons aren't included in that overall redox equation. Let's just do one more practice one to get into the rhythm of this. So here's one that you're going to need to do all the components of. Pause the video and give yourself time. Take your time for this one. Pop them up. So balancing the equations, you're going to go through your steps. Top equation obviously only needs 3 electrons. Next equation, it's already balanced the Cr for you. Then you need to add the water. So you need 7 H2O. Balance it on the other side with 14 H plus. That's going to give you plus 12 and plus 6. So you need 6 electrons on your left-hand side to balance that out. Obviously, those electrons are not equal. So you see that you need to multiply the top equation by 2. Once you've got that, you can cancel your 6 electrons out on the top and bottom and then write out your overall equation. So we're just getting to the point where we're rinsing and repeating, right? We're balancing the equation, using water, H plus electrons to balance our equations. Once you've got 2 balanced half equations, you make the electrons equal, and then you can combine them to give you an overall redox equation. So by popular demand, we're going to try an exam question here. So you've got 2 exam questions. Pause the video, give yourself some time. Okay, let's have a little go through these answers then. So the first question, kind of a lower level SL question. In this one, you're given both equations and you just have to balance those electrons, which means we're going to multiply the ion equation by 6. Once we've got the electrons balanced just as before, you're going to cancel those electrons, add everything on the left-hand side of both arrows together, and that is going to form everything on the right-hand side of both arrows together. With the second one, you're going to have to write out both of your half equations. So that's going to be your MnO4 going to Mn2+. In the end, you're going to have to multiply that equation by 2, and you're going to have to multiply your hydroxide breakdown equation by 5 to get rid of the electrons, which will give you this equation as your final answer. If you struggle a little bit with the half equations on that second one, go back earlier in the lesson to look at how to form half equations. Both of those equations were done earlier in the lesson if you just want to use that to practice as well. And as always, make sure you're doing a lot of questions with this to really get it down, and just remembering that silky smooth 5-step process. That is the golden road that is going to lead you to the answer. Thanks again for joining me. Comment, please give me some feedback, like, subscribe, hit the bell icon so you get notifications. And if you feel like procrastinating, if you feel like not doing work, check out the other channels and do the same there. Share the videos. And as always, guys, practice makes slightly better.